I'll try to illustrate the concept of compounding using some examples in Excel, and try to relate the present value and future value and all the interest rates together in a formula. So it's easy to remember, and in fact there's no need to memorize. Okay, so let's look at a very simple example. Suppose that someone wants to borrow $1,000 from you, and he'll repay $1,000 in a year's time, plus a certain interest rate. So you look at him and you think that, okay, based on his creditworthiness and the prevailing interest rate, and you decided to charge him 10% interest rate per annum. Okay, let's have some definition now. Let's R be the interest rate, and it's defined as 10%, as we mentioned just now. It's always defined in the annual terms. So R will be the annual interest rate. Let T be number of years that the loan is outstanding, so this will be 1. Okay, 1 number of years. And so T is always defined in number of years. Assuming it's a half-year loan, this T will be 0.5. If it's a quarter-year loan, this will be 0.25. If it's a 2-year loan, it will be 2, and so on and so forth. What else do we have to define? Okay, let M be the compounding frequency. And in this case, we don't have any compounding, so compounding is 1. What does compounding mean? Compounding basically means that is whether interest will be levied on interest that has been charged in the previous period. Okay, so as you go on, I think this will become clearer. Okay, so this $1,000 is clearly the present value, and we're trying to work out the future value that will happen in the future. Okay, so this is a straightforward example. In 1 year's time, you certainly hope that he'll return you the $1,000 plus certain amount of interest. So interest is calculated as 10% of the amount that you lend him. So it's 10% multiplied by $1,000. Okay, so this will give you $1,000 into 1 plus 10%. Okay, actually there's a, okay, never mind. So what's the answer? As expected, is $1,100. So this is the future value of $1,000 based on a 10% interest rate with no compounding, or rather just one compounding in a year. Let's look at the next example where it's slightly more complicated, and there's 2 compounding. Compounding frequency is 2, or rather it's semi-annual compounding, if you like to put it in another way. So let me copy this down. Okay, so in this case, it's exactly the same, but compounding frequency is 2. Okay, so when you see compounding frequency is 2, you've got to break down the interest rate here into the interest per period by simply dividing the interest by the number of periods. So in this case, annual interest is 10, number of periods is 2. In each period, the interest that we charge is 5%. Okay, so it's 5% here and 5% here. And when there's compounding, it's necessary to work out the amount owing in every period. So as at T over 5, we need to work out the interest that is owing at T over 5 time. So together with the principal, the amount that your friend owes you is simply $1,000, which is the principal, plus $1,000 multiplied by 10% divided by 2, okay, which is 5%. So this is the interest that he owes you as at T is equal to 0.5. Okay, Let's move on and look at the next period. At the end of 1 year, he owes you basically two things: the principal and interest that he owes you at the middle of the year, plus the interest that he owes you in the second half of the year. Okay, so let's write down the amount that he owes you as at the mid-year. Okay, so this amount is the owing at t equal to 0.5. Okay. Okay, so let's we need to calculate the interest that we want to charge him during the second half of the year. Okay, so this is slightly more involved because we are going to levy the interest based on the amount outstanding as at t equals 0.5. So this will be 5% of the amount that is outstanding as at t equal to 0.5. So it's simply 5% multiplied by this amount. Okay, so it should be clear, and the total amount that your friend owes you at t equal 1 is just the sum of these two. Okay, so it's this expression plus this expression. Okay, so just a bit of algebra here, and we can see clearly that this expression here, 1000 plus 1000 into 5% is the same as 1000 plus 1000 into 5% inside here. Okay, so we can simplify this into multiply by 1 plus 5%. Okay, so let me write this one in as 10 over 2, so it becomes clearer that 5% is a result of 10 divided by 2 compounding periods in the year. So actually we can simplify this further by doing this $1,000 multiplied by 1 plus 10% divided by 2 to the power of 2. Okay, so all these are the same. Let's work out this expression. Okay, this will be 1102.5, which is expected slightly larger than the previous simple interest example because of the second half, right, where we have interest calculation based on the interest that the borrower incurred in the first half of the year. So it's slightly more than the first example. Okay, let's move on to a slightly more difficult example where there are instead of 2 periods a year, we are compounding by 4 periods a year. Okay, let me copy this down. So instead of m equal to 2, we have m equal to 4, which means that we are levying interest, we are calculating interest every 3 months instead of every 6 months. Okay, so if you had followed me throughout the second example, this shouldn't be that difficult, but let me go through it anyway. So we are, as per previous two examples, we are using an interest rate of 10% per year. And if we have divided into a quarter, so there are 4 periods in a year, and what do you think is the interest rate per period? It should be 10 divided by 4, which is 2.5%. Okay, so instead of 5% in the previous example, 10% in the first example, we are now charging our borrower 2.5% every 3 months. Okay, so let me copy it. Okay, okay, so similar to the previous example, let's calculate the principal plus the interest rate that we are charging him as at t equal to 0.25. Okay, so principal is $1,000, and how much interest are we charging him? Is $1,000 into 1 plus 10% divided by 4. Okay, so this is the principal plus interest that we are expecting from our borrower as at t equal to 0.25. Okay, let's move on to t equal to 0.5. And as similar to what we did in the previous example, we have 2 components as at t equal to 0.5. Let me copy this down. Okay, so interest owing as at t equal to 0.25. Okay, which is this amount. Okay, and interest levied on the second quarter. This will be 0.25% of the interest plus principal owing as at t equal to 0.25. So it should be 2.5% multiplied by this full amount. Okay, and the total will be this plus this. I think I will cut through all the calculations and then just show you the results. The results will be simply $1,000 into 1 plus 10% divided by 4 to the power of 2. I hope you can see what I'm driving at. So this as at t equals 0.5 is very similar to this formula. Okay, except that the interest that we charge is now 2.5% instead of 5% in the previous example, because we are now talking about 4 periods instead of 2 periods. Okay, so we are now only at here. I think I'll skip and then move on to t equal 1, because this should be quite intuitive. So as at t equal 1, the final result is very similar to what we have here. The only difference is, instead of to the power of 2, we are now talking about interest for 4 periods, so it should be to the power of 4. Okay, let's look at the result of this one. Okay, so now we are looking at quarterly compounding. We have a future value that shows us $1,103.81, which is certainly more than the one that we saw just now, and which is more than the annual compounding that we saw in the first example. Okay, so you can see that as compounding frequency increases, the future value increases as well. Okay, let's look at the final example where we increase the number of years to 2. Compounding frequency is 2 as well, so it's a bit more different. Okay. Okay, let me copy down this number. Okay, so we have compounding frequency 2. Number of years, instead of 1 year, we are talking about 2 years. Okay. Let's look at this. So now we have semi-annual compounding as shown as here, 2. So make a guess, what do we expect? What interest do we expect in every period? Easy, right? It should be 10% divided by 2. So we are expecting 5% interest every period. It's basically arrive at 10 divided by 2 here. So interest for the first half of the year in the first year will be interest plus principal, so it should be $1,000 plus $1,000 into 5%. Okay, so as a t equal 1 is very similar to what we did just now. Let me copy this down. As a t equal 1, we have two components as well. So we have an principal and plus interest owing as a t equal to 0.5. Okay, this amount will be as calculated here. Okay, we have interest levied in the second half of the year. Of year 1. Okay, so this will be simply 5% multiplied by this amount, interest on interest. Okay, so and the final total will be the sum of these two, and as we worked out just now, it should be $1,000 multiplied by 1 plus 10% divided by 2 to the power of 2. Okay, so it should be clear that it's very similar to what we had just now. So I'll skip t equal to 1.5 and let's move on to the maturity of the loan. Okay, so it should be intuitive, and I'll skip all the intermediary calculation and just write down the final result, which is simply this one. Instead of to the power of 2, we have to the power of 4, because there are 4 periods in this whole of 2 years, and the final result is 1215.5, which is certainly more than what we have, because it's a 2-year loan instead of a 1-year loan. Okay, so just to end it all off, let's look at all the formulas that we have. This one, for the 1 year and no compounding. This one for the 1 year and 4 compounding, and this one for the 2 years and 2 compounding. And actually we can generalize based on all these formulas and try to link the future value and present value and all the interest rates. So we can see that, let me write down the final result. So the future value, let's call it FV, is simply the present value multiplied by 1 plus interest rate R expressed in the annual terms divided by number of compounding periods, let's call it M, and to the power of T multiplied by the number of compounding periods. Okay, let me put using asterisk instead of X. Okay, so this is the final result that I'm trying to drive at through using all the 4 examples that we went through just now. Okay, let's prove it. Let's look at this example where we have 1 year, 4 compounding periods, and interest rate of 10%. So using this using this formula, we have future value is equal to present value $1,000 multiplied by 1 plus R is 10%, divided by M, number of compounding periods, we have 4, okay, to the power of 4 multiplied by the number of years, 1. Okay, so the result will be 1103.81, which is what we have done here. Yeah, so you can work through these examples yourself and just to convince yourself that this formula is the correct formula to use. Okay. Okay. Lastly, I just want to run through with you guys the concept of continuous compounding. Okay, let's look at the formula that we went through just now. By running through another example, I want to vary the number of compounding, and by increasing it up to daily and even hourly compounding, and take a look at the results. Okay, we have the same variables that we mentioned just now, T, which is the number of periods where the loan is outstanding. Let T equal 1 for keeping simple. We have the present value, and instead of 1,000, let us use $1. The interest rate 10% as per just now. Okay, so just now we have M and we have the future value. Let's vary the M and look at the effect of M. Of course we know through the examples just now, as M increases, the future value increases because we are compounding more interest rates over more periods. Okay, so but I just want to go through with you and arrive at the concept of continuous compounding. Let's look at M equal 1, which is the 1 year in the first example that we went through just now. M equal 2, semi-annual compounding. M equal 4, quarterly compounding. 12, monthly compounding. Okay, and we have daily compounding as well. Let's look at let's assume it's 365 days in a year. Different markets have different concept of annual compounding. Some markets use 255. So maybe Middle Eastern market are different, Asian market are different. So you got to be very careful when depending on the market that you trade in. Okay, then what else? So this is daily compounding. Let's look at a bit more closer to continuous compounding. Let's look at hourly compounding even. Okay, it's 365 multiplied by 24 hours in a day. So this will be 8760 compounding. Okay, let's look at the future value based on $1, based on all these various compounding frequencies. Okay, using the formula that we went through just now, is basically future value is equal to the present value multiplied by 1 plus interest rate divided by the compounding frequency to the power of number of years multiplied by the compounding frequency. Okay, so let me copy the formula over. Okay, so let me show you, copy the problem down as well. Okay, so we can see as per what we have shown just now, as compounding frequency increases, the future value increases. So we have 1.1 here, 1.1025, 1.10381, and so on. Okay, let me show you what is exponential. Exponential is a mathematical formula which has very interesting interesting characteristics. Okay, so magically, or what, the exponential of the interest rate should be interest rate multiplied by time. Okay, which will become very close to the compounding hourly result. As we move on into compounding hourly, compounding by minute, by second, and so on, we will have a value which is very close to the exponential of the interest rate multiplied by time. Okay, so this is what we call continuous compounding. Compounding by a time which is to the limit, which is very close to 0, milliseconds and so on. Okay, maybe I'll show you a proof later, but I just want to illustrate why continuous compounding is very widely used in the finance industry. Because when we integrate or differentiate the exponential function, the result is the same. It's an exponential function. Okay, so let me write down what I mean. When we differentiate an exponential function, the result is the exponential function. Or even when we integrate an exponential function, the result is also the exponential function itself. Okay, so this is a very useful result as we move on into a more complicated, more involved aspect of finance valuation or even risk management. But for now, just understand that the exponential function means it's a continuous compounding. And you may ask, why do we use continuous compounding even though the actual practice and actual contractual agreement between you and the borrower is not continuous? Let me illustrate by using a lower interest rate, like the interest rate environment that we are seeing now, which is very low. In fact, interbank or even treasuries interest rate can go as low as 0.25. Okay, so let us look at the 0.5 interest rate. Okay, you can see that regardless of what's the frequency of compounding, is always very close to 1.005. Okay, so which clearly illustrates that it doesn't matter the frequency of compounding when the interest rate is very low. We can simply use an exponential function to approximate the result based on the compounding, higher compounding frequency. Okay, so that's why in the financial market, people conveniently use the exponential function to calculate present and future value. Yeah, so just for as a added interest, let me show you the graph of an exponential function. Okay, interest rate R, the exponential function based on the interest rate R. Okay, let's vary the R from 0.5 all the way to 1.5. Let me plot the graph. Okay, so we can see that the graph is increasing in a very significant manner as the interest rate move larger and larger, and when interest rate is 0, the function cuts the y-axis at 1, which is understandable because one refers to the principal, so there's no interest element when interest rate is 0. Yeah, when interest rate is negative, the future value will become a smaller amount, and yeah, so that's basically what I want to illustrate here. I think lastly, I just want to show you a proof of why as the compounding frequency increases, the result will end up to be the exponential function. It is just for interest sake. So let me write down the formula again. Okay, so this is the result for the present value, and of course you can just play with the formula and then arrive at the result for present value, which is equal to future value over 1 plus r over m into m plus t. Okay, so you can play around with this formula, and in fact you can take r out to be expressed as a future present value and compounding frequency and time. Okay, so when we talk about continuous compounding, this m value, you can treat this m value as going to infinity because they are so frequent compounding that this m becomes very, very large and it tends to infinity. So let's rewrite the continuous compounding based on this formula as m tends to infinity. Okay, so this will be equal to PV. We have this thing called a limit as m tends to infinity, okay, of this expression inside here, 1 plus r over m times t. Okay, so this is already in itself a continuous compounding formula. We can let u be m over r. Okay, so when m tends to infinity, u tends to infinity as well. Okay, because m is in the numerator, so this one can be written as present value into limit u tends to infinity 1 plus 1 over u to the power of this mt, right? So it becomes ur, okay, urt. Okay, so this expression, if you look at, let me change the color. If you look at this expression, this is in fact if you solve this expression, this will become exponential function. This becomes the exponential function, exponential to the power of 1. So if you are interested, you can go and put it into Excel with a very large u, and you can see that this will result in a number which is very close to e to the power of 1. So let's say if we put u equal to say 10 million, you'll almost be exactly equal to e to the power of 1. Okay, so this one, let me write the next step. So this one will become e to the power of rt, okay, which is the solution for continuous compounding. So let me recap. So the solution for compounding by days, months, quarterly, and so on will be this one. And if you go up into very frequent time, the continuous compounding, we should use this formula. Okay, PV into e to the power of RT. Okay, so this future values will be this one. So you can play around with this formula again by trying to find out what is R. So let me move the variables around. ERT is equal to FV over PV. Okay, so which implies that RT is equal to the natural logarithm of FV over PV. Okay, as you move on in the finance, you will find out that this function is very commonly referred to as the returns function. So the future value over the current value, and you take a logarithm, and this will be the returns for that period. Okay, this is for interest sake, and maybe we'll go through some of these examples in the future lecture. Okay, that's all for now. Thank you.